Today we are going to discuss classification algorithms that are statistically based. These are going to use statistical techniques in order to assign data items to a particular class. At the end of this session, the student will be able to demonstrate various classification algorithms which are based on statistics and compare between these algorithms. We categorize algorithms of classification into three categories. The first one is statistical algorithms based on the use of statistical information. Second, distance-based algorithms which use similarity or distance measure. Third, rule-based algorithms which use the if-then rules. The statistical-based algorithms are based on statistical measures, and we are going to relate our particular data based upon these values which they are having to be generated by a statistical measure. The first technique is regression, which deals with estimation of an output value based on the input values. So in our data, we are going to consider some values as input values and some values as output values. The input values are from the data set D. The output values are also values that represent the classes now. And regression can be used for forecasting what the output should be from the input which is available to us. Regression takes a set of data and fits the data to a formula. So we'll have input data and we'll have output data, and we'll try to find a relationship between this input data and output data with a formula which we will be designing. And simple regression can be thought of estimating the formula for a straight line. Now let us think and find out for ourselves what is a straight line and what is the formula for the straight line. So two answers come into our minds. One is it divides the full space into two parts, and second is y is equal to mx plus c is the equation of a straight line. Therefore, regression can be equated by partitioning the data into two classes. The straight line is a break-even point or a division between the two classes. If you look at this formula, y is equal to c0 plus c1 x1 plus dot dot cn xn, it resembles the equation of a straight line y is equal to mx plus c, where x is taking different values and there is a coefficient attached to the particular x, and c0 is a constant. To determine the regression coefficients is our importance c0, c1, cn, and find the relationship between the parameters y and the input x1 to xn. It is similar to y is equal to mx plus b. Given 2 points in the xy plane, m and b are the regression coefficients now. The 2 points represent the training data, and actual data points do not fit the linear model exactly, because actual data is true data which may not be always linear. So the model generated is an estimation of the actual input output relationship. So we generate a linear model and we use it to predict an output value given an input value. If we attempt to fit non-linear data with this model, there will be poor results. And also we have to keep in mind that all the data of the real world is not linear data. So the drawbacks of this particular algorithm is data do not fit a linear model, Linear model may be poor because of noise or outliers which are affecting your particular data. Noise, as we know, is erroneous data. Outliers are exceptions to the usual or expected data. And now the observable is described by y is equal to c0 plus c1x1 up to cnxn plus an error, which is a random error having a mean 0. So the accuracy to fit of linear regression model to actual data can be estimated using a mean squared error function, finding the difference between actual and estimated, which is your error, and finding a square of this. So the approaches are, first we may use a division method where data is divided into regions based on classes. Now, if each of this data is an isolated region based data, data is plotted in n-dimensional space without explicit class values shown. Regression divides this space into regions of one per class. And if we use prediction, formulas are generated to predict the output class value, and a value of each class is included in the graph. Regression generated formula for a line to predict the class values. However, all real world data, as I have already told, is not linear. So we will go for the next form of regression called as logistic regression, which may be used to fit data using logistic curves where linear regression does not work. The second statistical method is Bayesian, and we are going to use here the naive-Bayes technique, which has assumptions that contribution by all the attributes in our data set are independent. So each column contribution in our data set is going to be considered, and our rows in our data set are going to be our tuples of our data set, and each contributes equally to the classification problem. So naive-Bayes classification is based on the Bayes rule of conditional probability, based upon how much we can believe and how much we can disbelieve in the existence of a particular variable. So given a data value xi, the probability that a related tuple ti is in the class Cj is determined by conditional probability Cj given xi. Training data is used to determine p of xi, and conditional probability of xi given Cj and the probability of Cj when fitted into the Bayesian formula is going to give you an estimate. So estimator posterior probability P of Cj given xi, and then probability of Cj given Ti is supposed to be calculated. Now what is the method? The first step, estimate the probability which is prior, that is probability of Cj for each class by counting how many different class occurs in the training set. Then for each attribute xi, the number of occurrences of each attribute value is counted to determine p of xi. And in the third step, we estimate the probability, which is conditional, probability of xi given the class Cj by counting how many or how often each value occurs in the training data. So we look at the attribute values here, and the tuples in the training data have many attributes with many values, and we use to these derived probabilities when the new tuple must be classified. Thus it is probability based. So naive Bayes is both descriptive and predictive in nature. So from these particular algorithms, we remark that probabilities are descriptive and used to predict the class membership for a target tuple. When classifying target tuple, conditional and prior probabilities from the training set are used to make the predictions, and we combine the effects of different attribute values from the tuple. Now, what are the advantages of using naive Bayes? It is easy to use. Only one scan of training data is required. It easily handles the missing values by omitting probabilities. So here we are omitting probabilities which are of those items which are going to have very less probability of occurrence when calculating the likelihoods of membership. So you could omit the missing values. So missing values and classifications are dealt with here, and for simple relationship, it yields good results. Therefore, now we think about when we could design a linear relationship, we prefer to use regression. When we are dealing with probabilities, we are going to use the naive-based algorithm, okay, and naive-based techniques. The disadvantage is that it does not always yield satisfactory results because the attributes are usually independent. We sometimes use subset of attributes ignoring those that are dependent on others. It does not handle continuous data. However, in the real world, most of the data is continuous in nature. Even after dividing this data into ranges, it is difficult since the division of domain into ranges is itself difficult and impacts results. Therefore, there is a restriction of using such techniques. I have referred for this presentation. Thank you